We are going to do some tutorials based on biomass combustion. So this is our first problem to be solved. A dry biomass has following composition on mass basis: carbon 40%, hydrogen 5%, oxygen 30%, and ash 25%. Determine the stoichiometric oxygen requirement for the combustion of this biomass. Assume that the ash is inert. An average molecular weight of ash is given as 56. And if the ratio of nitrogen to oxygen in air is 4:1 by volume, also determine the stoichiometric air requirement. So this is a typical problem. We have biomass composition is given and on dry basis, so there is no moisture, and we have to find out first the stoichiometric oxygen, that is the chemically correct oxygen for complete combustion of this biomass. Then by assuming that we have 4:1, that means 80% nitrogen and 20% oxygen in air. Also we have to find the stoichiometric air requirement also. So this is a typical problem. This type of problems may be asked in biomass combustion. So what is our first step? First step, we have to find the molecular formula of the given biomass. Then only we can find the stoichiometric oxygen and air. So now we are assuming for 100 gram. So consider 100 gram of dry biomass. What will be the mass of carbon? It will be 40 gram, because it is given that the carbon is 40%. So if you take 100 gram biomass, carbon will be 40 gram. That means the number of moles will be 40 divided by 12. So 12 is the molecular mass of carbon. So we are getting as 3.33 moles. Similarly, we can find the other elements also. Hydrogen is 5 gram and its molecular weight is 1. So number of moles will be 5 divided by 1, 5. Oxygen, we have 30 gram. So 30 divided by 16, the molecular mass of oxygen is 1.875 moles. So please take care that here we have to take only oxygen atom, not oxygen molecules, because in the molecular formula it will be CHONS like that. So we don't have to take O2 here, because this is for finding out the molecular formula of biomass. So that is why we are taken only 16. So 30 by 16, it will be 1.875 moles. And finally we have ash 25 gram and its molecular mass is given as 56. So 25 by 56, 0.4464 moles. So we have find out the moles of different elements in the biomass. So the molecular formula, it will be like this: carbon 3.3, hydrogen 5, oxygen 1.875, and ash 0.4464. So now we can write the stoichiometric equation. First we can write the stoichiometric equation oxygen only. So, and also we know that ash does not take part in any of reaction. So the equation will be like this. This is our biomass plus some d moles of oxygen, combustion oxygen. We are converting it completely to water and carbon dioxide. So these are the main products here: water and carbon dioxide. And ash will remain as such. Here we have g moles of ash, so that g moles of ash will remain as such in the reaction. Now we have to find out the unknown quantities here. So we can replace the biomass. Already we have find out the molecular equation of biomass like this. So we can replace this by our biomass molecular formula, plus dO2 is equal to E moles of H2 and F moles of CO2. So we have to find D, E and F. These are the important moles. We have to unknown moles. We have to find out D, E and F. So ash is inert, so it does not matter what is the G value. Now we are going to find this D, E and F. So that is by balancing carbon, hydrogen and oxygen on both sides. So first we have to consider carbon balancing. So if we are considering carbon balancing, what will be the left side? We have 3.33. So right side only F moles of carbon is there. So that means F is 3.33. So by balancing carbon, we are getting F is equal to 3.33. Then we have hydrogen balance. So again we have to consider the hydrogen balance from both sides. So here we have 5 and right side we have 2E. Here 2 moles of E. So 2E is 5 means E is 2.5. So we have find out E and F. Now the only thing remaining is D. So this D is very important because it determines the stoichiometric oxygen quantity. So for that we have to go for the oxygen balance on both sides. Here we have 1.875 oxygen plus 2D. So we are taking oxygen atom. So here 2D moles of oxygen atom, that is equal to here E oxygen. This is water. We have E moles of oxygen atom plus here we have 2F moles of oxygen atom in carbon dioxide. So this is our equation for balancing oxygen. 1.87 plus 2D is equal to E plus 2F. Now already we have find out E and F 3.33 and 2.5. Substitute that in this particular equation. We will get 2D is equal to 2.5 plus 2 into 3.33 minus 1.875, that is 7.285. So D is 3.6425. So we have find out the all D, E and F. D is 3.6425. Now we can find out the 100 gram of biomass, what is the oxygen requirement, because we have find out D, the mole of oxygen. The D is, we are finding out just 3.6425. So what will the mass of oxygen then? So if you know mole, the mass will be mole into molecular mass, the oxygen atom. So here we have to take the oxygen molecule because this O2 is coming in this equation. So that we have to be take care of. In the previous one, for determining the molecular weight of biomass, we have only O, that is oxygen atom. So that is why we are does not take mass as 32, we are taken as 16. But for this stoichiometric air mass calculation, we are in the equation we have O2. So we have to take 32. So that means 3.6425 into 32, 116.56 gram. So that is the mass of oxygen required for 100 gram of biomass. Or we can say 1 gram of biomass will be 1.1656 gram of oxygen. So that is the stoichiometric oxygen requirement. Now we have to find the stoichiometric air requirement. Mostly in practical case we will be combusting with the help of air, not oxygen. So in this problem it is asked that air consists of 4:1, that is nitrogen 80% and 20% oxygen. So we can find out the air, nitrogen in this air containing 3. So if the oxygen mole is 3.6425, then what will be the, if you are taking air, what will be the nitrogen? So nitrogen also will be coming with oxygen. How much mole of it will be? 4 into 3.6425 because air contains 4:1 nitrogen. So for 1 mole of oxygen we will have 4 moles of nitrogen, and we have already find out the stoichiometric oxygen requirement as 3.6425 moles. So nitrogen present for that corresponding mole of oxygen will be 4 into 3.6425, that is 14.57 mole. Now we can find out the mass also. This is the mole of nitrogen present in that air. Now mass will be again mole into molecular mass of nitrogen. So here we have to take the nitrogen molecule N2. So 14.57 into 28, that is 407.96. So this much mass of nitrogen will be present in the air. Now what will be the total mass of air? This plus oxygen. So that will be the total mass of air. Nitrogen, mass of nitrogen plus mass of oxygen. So total mass of air will be this 407.96 plus 116.56. So it will be 524.52. So this much mass of air is required for complete burning of our biomass, 100 gram of biomass. So obviously for 1 gram, this is for 100 gram of biomass, for 1 gram it will be 5.2452, or we can say the stoichiometric air fuel ratio in this case will be 5.2452. So just compare this with your IC engine. We have studied IC engines, petrol, diesel. What is the stoichiometric ratio for petrol and diesel? So they are around 15:1 to around 16:1 in that range. And you can see the biomass, most of the biomass, the stoichiometric air fuel ratio will be in this range, that is 5 to 6. So that is the stoichiometric air fuel ratio of most of the biomass. So we have find out the stoichiometric oxygen requirement as well as stoichiometric air requirement. Now we have to solve another problem. A biomass has following composition on mass basis: carbon 35.5, hydrogen 4.8, oxygen and 25, nitrogen 0.4, sulfur 0.15, chlorine 0.55 percentage, and moisture we have 26 percentage, and ash is 7.6 percent. Assume the average molecular weight of ash is 56. So if in the question the molecular mass of ash is not given, we can take it as around 56, because the ash will be the, already we have studied the oxides of sodium, potassium, etc. Mass is in this range. And if this biomass is burned in a fixed bed combustor, what will be the composition of flue gas if 20% excess air is supplied? So this is a difference between this problem and previous one. Here we have more elements. In that only we have carbon, hydrogen and oxygen. Now we have nitrogen, small amount, sulfur also is there, chlorine also is there, and here we have also moisture. So that problem we have considered dry biomass, but here we have 26% of moisture. And in this we have to find out the flue gas, that is a product gas composition, how much percentage of carbon dioxide, how much percentage of water, etc. So this, and here also we are providing 20% excess air. So normally already we have discussed in practical we will be supplying excess air other than that stoichiometric air. So now we have to solve this step by step. So here also we have to consider 100 gram of biomass for our simplicity. What will be the mass of carbon? It will be 35.5 gram, because the percentage is given by mass. And again we have to find out the molecular mass, molecular equation of biomass. So first you have to take carbon is 35.5 gram. So 35.5 divided by 12, it will be 2.958 moles. Then hydrogen 4.8 gram. So 4.8 divided by 1, 4.8 moles. Oxygen we have 25 gram. So 25 divided by 16, 1.5625 moles. And nitrogen is very small percentage, that is 0.4. So 0.4 divided by 14, we have 0.0286 moles. Sulfur we have 0.15. So it will be molecular mass of sulfur is 32. So it will be 0.15 divided by 32, 0.00471 moles. So we have find out this moles. Now moisture and ash is remaining. Chlorine also, chlorine is 0.55 gram, and the molecular mass of chlorine is 35.5. So we have to remember this molecular mass of some basic elements like carbon, nitrogen, oxygen, nitrogen, sulfur, etc. And chlorine is 35.5. That is 0.0155 moles. And moisture is 26 grams. So moisture means it will be water, H2O. So our water mass is, molecular mass is 18. So 26 by 18, 1.44 moles. And finally we have ash, 7.6 gram, and its molecular weight is 56. So 7.6 divided by 56, it is 0.1357 moles. So this is the all moles. Already we have calculated the mole of different elements in biomass: carbon, nitrogen, oxygen, nitrogen, sulfur, chlorine, moisture and ash. Now we can represent our biomass in equation form. So that will be this: carbon 2.958, hydrogen 4.8, oxygen 1.5625, nitrogen 0.0286, sulfur 0.0047, chlorine 0.0155, and ash 0.1357, and moisture is 1.444. We can further simplify this equation, because moisture means it is water. We have 2 moles of hydrogen, so we can add this 2 into 1.444 with the already we have hydrogen atom here, so we can further simplify this. Similarly, oxygen also we have 1.44 moles here. We can add that 1.44 with this oxygen atom, that is 1.5625. So that will be better for writing the equation. So further we can add this moles of water, hydrogen and oxygen, and this will be like this. So carbon is same 2.958, but hydrogen is now 7.688. So how it is 7.688? That is 4.8 plus 2 into 1.444. And similarly oxygen is changed to 3.0065, because we have 1.5625 of oxygen here plus 1.444, and the remaining things will be same. So this is our modified equation for biomass. Now our combustion reaction. What will be our combustion reaction? This is our biomass: carbon, hydrogen, oxygen, nitrogen, sulfur, chlorine and ash, plus G moles of oxygen. We don't know the stoichiometric oxygen requirement. And product side we will have carbon dioxide, obviously we will have water, and other than that we will have nitrogen dioxide, because here in this problem with some small amount of nitrogen is present in biomass, that will be converted to nitrogen dioxide. And here sulfur dioxide also will be there, because sulfur is present in trace amounts, and chlorine will remain as such, and ash also will remain as such. So this is a typical equation for this problem. So just remember this, or compare this to the previous problem. Previous problem we don't have any nitrogen, sulfur or chlorine, etc. So that is why in that problem we does not have any nitrogen dioxide or sulfur dioxide. Now again we have to go for the balancing. So this is our case. This is already we have find out the molecular formula of biomass, plus oxygen will be this. Now we have to go for the balancing of atoms on both sides, just like the previous problem, so that we can find out these unknown quantities like G, H, I, J, K, etc. So first we have to go for the carbon balance. Carbon balance we will get H, right side we have only H mole of carbon, that is equal to left side we have only this 2.958. So H is 2.958. Now we can go for the balancing of hydrogen. So the left side we have 7.688 moles of hydrogen, and if you look at the right side we have 2I moles of hydrogen here. So 2I is equal to 7.688, or I is 3.844. So we have find out the moles of hydrogen also. I is 3.844. Now we can go for the balancing of nitrogen. So remember, the oxygen balance should be done last, because the oxygen is coming in most of the terms. You can see here we have oxygen, here we have oxygen, here we have oxygen, here we have oxygen. So most of the term are containing oxygen atom. So you can find out only that in the last step. So we have to go for nitrogen next. So balancing of nitrogen, here we have 0.0286 of nitrogen, and right side we have J moles of nitrogen. So J will be 0.0286, and again balancing of sulfur 0.0047, that is equal to K moles in the right side. So K is 0.0047. Then balancing of chlorine, we have this 0.0155, that is equal to 2m. So m is this one, 0.00775. Now balancing of ash. So ash is inert, so this ash 0.1357 ash will be remain as such as n moles. So n is 0.1357. So we have find out all other unknown quantities. Now the oxygen is remaining, so we can go for oxygen balance last. So what will be the oxygen balancing? So here we have 3.0065 oxygen atom. So 3.0065 plus here we have 2G moles of oxygen atom. So 2G, that is equal to, now first term carbon dioxide, we have 2H moles of oxygen atom. So that is equal to 2H plus, here we have this 2I, sorry, I is there, only I is there. In water we have I moles of oxygen atom, so plus I. Nitrogen dioxide we have 2J moles of oxygen atom, so plus 2J. Sulfur dioxide we have 2K. So this will be our equation by oxygen balancing 3.0065 plus 2G, that is equal to 2H plus I plus 2J plus 2K. Now already we have find out HI, J, K, G, etc. Only we have to find the G. So substitute that. So we will get like this. This is equal to 9.8266. Substituting all HI, J and K. And that means G will be, further simplifying, we will get G as 3.41005. So all other quantities are known quantities, HI, J and K. Substitute and solve, we will get G as 3.41005. So we have find out the stoichiometric oxygen requirement, that is 3.41005 moles of oxygen. But in the problem it is given that we are supplying excess air, so 20% excess air is supplying. So stoichiometric mole is 3.41005, but in this problem we are supplying excess air or excess oxygen, so that will be 1.2. We have to multiply this mole with 1.20, because we are providing 20% extra oxygen, so that will be 4.0926 moles. So this is the total number of moles we are using as oxygen. Now again we are, if we are considering air we know we can assume 20% oxygen and 80% nitrogen, or also in the most accurately we can say 21% oxygen and 79% nitrogen, but here we can take 20 and 80. So nitrogen will be this much mole into 4, because 4 times 1 mole of oxygen we will have 4 moles of nitrogen in air. So 4.09206 moles of oxygen means nitrogen will be this much, 16.3684 moles. Then what will be the mass of air? Mass of air will be this nitrogen moles into its molecular mass, that is 28, plus this oxygen moles into molecular mass of oxygen, that is 32. So that will be 589.26. So mole of nitrogen into molecular mass of nitrogen. Remember, here we have to take the nitrogen molecule, because the air, the oxygen and nitrogen will be in molecules. So into 28 into 32, the mass of oxygen molecule. So we will get 589.26 for 100 gram of biomass. First we assume the 100 gram of biomass. So what will be for 1 gram of biomass? This will be 5.8926. So here again we are getting the air fuel ratio around between 5 and 6 for this biomass. This little bit higher, that is 5.8926 compared to previous problem. And now we have to determine the flue gas combustion. So already we have find out the moles of the different elements, but we have to convert that into percentage, because gas will be measured as percentage by volume by different gas chromatography and analyzer. So we have to represent like that. So what will be the gas combustion of flue gas? Already we have find out this moles. Carbon dioxide, the right side carbon dioxide mole is 2.958, water is 3.844, nitrogen dioxide is 0.0286, sulfur dioxide is 0.0047. So all these things are obtained from that balancing. Chlorine is 0.00774 moles. But we have to add nitrogen. So in that equation, the previous equation, we have considered only oxygen atom. Sorry, oxygen only, not air. But in actual case, it's air. So that this nitrogen also will be present. We are assuming the nitrogen in air as inert. And it is almost correct, because in air, the nitrogen in air will react with oxygen only in very, very high temperature, more than 1500 degree. So that assumption will be mostly correct. So that nitrogen will be present as such in the exhaust or flue gas. So we have to take that also. So all these things, the remaining things are in the previous equation, stoichiometric oxygen calculation. This is from stoichiometric air calculation. We have moles of nitrogen is 16.36824, and the excess oxygen will also be present as flue gas. So how much that will be? So actually in flue gas, for stoichiometric equation there are no oxygen, because it is the chemically correct oxygen for complete burning. But if you are here, you are supplying excess oxygen, so we can say 0.20 moles of oxygen will be present in the exhaust or flue gas. So excess oxygen in the flue gas will be this mole of oxygen, that is 3.41005 into 0.2. that you have to take care. Here it is not 1.2, it is 0.2, because we are calculating the flue gas combustion. So in the flue gas, that excess oxygen will be present as such. The remaining oxygen are consumed by the biomass for the converting it to product. So this will be 0.68201 moles. So all these things will be present in flue gas. So carbon dioxide is there, water is there, nitrogen dioxide is there, sulfur dioxide is there, chlorine is there, and nitrogen, inert nitrogen molecule is there from the air, and we have some excess oxygen, that is 0.68201. Now we can add all these moles. For finding out the total moles, we have to add this. So total moles, if you add all these quantities, it is 23.8329. that is this 2.98, this plus all this we have to add. We will get 23.8932. Now we can find out the percentage of each gas. Just divided by this mole by total mole into 100 percentage, because volume percentage, we have to represent each gas as volume percentage, that is same as this mole percentage, because in measurement while doing gas chromatography and other equipments, our gas will be measured as this volume percentage. So the combustion of flue gas will be CO2 2.958 divided by this total moles 12 percentage, water again 100 into 3.844 divided by 23.89329, 16 percentage, nitrogen dioxide 100 into 0.0286 divided by total mole 0.119 percentage, sulfur dioxide is again 0.019 percentage, chlorine is very small quantity 0.032 only, and nitrogen. So if you are using air for combustion, this is the problem. Mostly our product will be inert nitrogen, that is 100 into 16.38824 divided by 23.893 is 68.5. So around 70 percentage we are getting as nitrogen itself, and 12 percentage is carbon dioxide, 16 is water vapor, and excess oxygen will be 2.85 percentage. So we have find out the combustion of flue gas. So like this you have solve these similar problems, and you can find the combustion of flue gas, in particular biomass combustion. Now we can go for one more problem. This is a different problem. We have the combustion of flue gas on dry basis from a combustor is as follows: 12.3 percentage carbon dioxide, 5.1 percentage oxygen, and the rest is nitrogen. From this data, calculate the weight ratio of hydrogen to carbon in the biomass, the percentage of carbon and hydrogen in the dry biomass, percentage of excess air used, the mole of exhaust gas discharge per unit kilogram of dry biomass. So this is a different problem. In this, the flue gas combustion is given, and we have to find out the some combustion of biomass, not like the previous problems. The previous problem, the biomass combustion was known, and we have to find out the flue gas combustion, but here the flue gas combustion is given on dry basis. So just we have to take in mind this on dry basis, that is why there is no water, it is dried out. So actually the water also will be present, but for while measuring this is dried. So how to find out these answers? We can do this step by step. So again here we have to consider 100 mole of dry flue gas. Just like previous problem, we have considered 100 gram of biomass for our simplicity. So here we have to consider 100 mole of dry flue gas. So in that, how much mole of carbon dioxide will be there? It will be 12.3. So 12.3 percent, that means 12.3 mole of carbon dioxide is present. 5.1 percent oxygen, that is 5.1 mole of oxygen is there, and the remaining is inert nitrogen. That means 100 minus these two quantities, 12.3 and again minus 5.1, that will be 82.6. So 82.6 is inert nitrogen, and we can assume the air contains 79% nitrogen and 29% oxygen by volume. So what will be the oxygen available? So we have nitrogen remains as such in the product side as well as reactant side. So this is the mole of nitrogen present, that is 82.6 mole. So what will be the, we can find out what will be the oxygen with supplied air, that will be 82.6 into 21 divided by 17, and that is 22 moles. Here we can assume in the previous problem we can also assume 80 to 20, that will be 4:1 we can take if you want. Then this will be 1/4. but here we are taking 21 by 79 for more accurate results. So this much mole of oxygen will be present in the supplied air. So nitrogen is 82.6 means oxygen will be obviously 22 moles. And in this oxygen, how much is the consumed oxygen consumed during combustion? We have, because 5.1 oxygen is remained in the flue gas, so the remaining will be consumed. So that will be 22 minus 5.1, 16.9. So this much mole of oxygen is consumed in combustion. So remember, we have supplied 22 moles of oxygen, and in that 5.1 is present in the exhaust. That means it is not consumed by any of the reactants. So what will be the mole of oxygen consumed will be 22 minus 5.1, 16.9. And again we can see from the flue gas composition, it is evident that the biomass does not contain sulfur, chlorine and nitrogen. So there is no sulfur dioxide or other nitrogen dioxide or chlorine. So that means biomass also will not have any of these elements. Now for consider this combustion reaction, what will be the combustion of carbon? It will be followed by this reaction. Carbon, 1 mole of carbon reacts with 1 mole of oxygen to form 1 mole of carbon dioxide, and the combustion of water or hydrogen will be followed by this reaction. 2 moles of hydrogen reacts with 2 moles of oxygen to form 2 moles of water. So we can use these two equations for further solving this problem. How? Because we know we have 12.3 moles of carbon dioxide present in the flue gas, that is given by the question. So how much mole of oxygen will be used for converting carbon? It will be 12.3, because 1 mole of carbon dioxide is produced with the help of 1 mole of oxygen molecule. So that means 12.3 mole carbon dioxide present means the carbon has used 12.3 mole of oxygen. So that means 12.3 mole of oxygen is consumed by carbon during combustion. Then what will be the mole of oxygen consumed for this reaction or water? That we can find out. We know what is the total mole of oxygen supplied, that is 22, minus 12.3 is the oxygen used by carbons, and minus 5.1 is the excess oxygen present as such in the product. So this will be 4.6 moles. So 4.6 mole of oxygen is used by hydrogen and 12.3 mole is used by carbon. And what will be the mole of hydrogen present? So if the hydrogen use 4.6 mole, we can use this equation. 2 moles of hydrogen is used by 1 mole of oxygen to form 2 moles of water. So this is the 4.6 mole of oxygen, means hydrogen present in biomass will be 2 into 4.6, that will be 9.2. So this is the method we are using for finding out the mole of carbon and hydrogen in biomass. So we are using these two equations and comparing the moles on both sides. We can say how much mole of carbon was there in biomass and how much mole of hydrogen is present in biomass. So weight of hydrogen will be this 9.2 into 2, 18.4 gram. Weight of carbon in biomass will be this 12.3 into 12, 147.6. So our biomass is consisting only carbon and hydrogen, because there is no nitrogen dioxide, sulfur dioxide, chlorine or other things. So the molecular weight of biomass will be 18.4 plus this. Adding these two, we will get 166 gram. So that is the mass of or weight of biomass. And hydrogen to carbon ratio, that will be this ratio. Hydrogen to carbon ratio will be 18.4 divided by 147.6, 0.125. And what will be the percentage of carbon in dry biomass? again it will be 100 into carbon is 147.6 gram divided by total mass of biomass, that is 166. It is 88.92 percentage. So that much percentage of carbon is present in dry biomass, and percentage of hydrogen in dry biomass is 100 into this 18.4. 18.4 is the mass of hydrogen in biomass divided by total mass, that is 11.08 percentage. And excess air supplied, we have find out percentage of excess air will be 5.1 divided by this 22 minus 5.1, that is 13.18 percentage. Because excess air, this is the mole of excess air present divided by the total moles consumed, that is 16 points by minusing this, so we are getting 13.18 percentage. That is the excess air supplied. And finally the mole of exhaust gas per kilogram of biomass. So how much biomass is present? 166. And flue gas, we have assumed initially we have 100 moles of flue gas we are assumed, so 100 plus this additional 9.2, so that we have to add, that is the, because water we are, it is dry biomass, so that means we are there is no water, but we have find out the mole of water, that is 9.2, that similar to the mole of hydrogen. So we have to add that 100 plus 9.2 divided by 166, it is 0.658 moles per gram. So you might have think why we are here 9.2 is coming, because the question, it was on dry basis, the flue gas, there is no water vapor, but actually there will be water vapor present, and we have taken 100 moles of flue gas plus water vapor present is, from this equation we can find out that how many moles of water vapor is there, because it is 9.2 moles. So we have to add that 9.2 here. So this is our answer. So with this we are stopping this tutorial. Thank you.